When you're sharing in Zoom, but what are you sharing with Airtable? Yeah, that's fine. Sure. There we go. Totally fine. Okay. Thanks everyone for joining us for the 2DCC webinar today. Our speaker is Shengxi Huang from Rice University. And Shengxi, just prompt me whenever you're ready for the next slide. We should be, let me make sure that I can get rid of this. How do you get rid of the side thing? Where's the button? Okay, just do this. Yeah. So let's do this. I'd put there. Is that okay?
And minimize, yeah. Mm-hmm. No, the minimum, yeah.
That's okay. You can move it. Perfect. Shengxi, you're good to get started.
Okay, yeah. So should I get started?
Yes, please.
Yeah, okay, yeah, thank you for the invitation. It's my great pleasure to be back at Penn State virtually, and I would like to share with you some of our recent progress on designer 2D materials and how we use it for multiplexed biosensing and how we actually use machine learning to assist the characterization of these materials. So next slide, please. Next slide.
You can go down to the lower, oh, you got it.
All right, so yeah, so current, so far there are lots of diseases that people do not have a good understanding about. And one of the typical examples is Alzheimer's disease, or AD. AD currently affects over 6 million people in the United States, and in the world, this number is over 50 million. It kills more than breast cancer and prostate cancer combined. Just in 2023, AD cost over $340 billion a year in the United States. And if the trend of AD does not stop, by 2050, the cost of AD would rise to the astounding $1 trillion a year. And so far, if a patient is diagnosed with AD, he or she is typically already in the late stage, and the disease progression is not reversible. This is mainly because we still lack a good understanding about AD, and we still have not fully identified the early diagnosis biomarkers. And therefore, we will need some biosensing technologies that can help us diagnose AD in the early stage. Please note here, for early diagnosis, just to improve the sensitivity is not enough because we don't even know what to detect. We don't know their biomarkers. And therefore, we will need some sensing technologies that can help us better understand the pathology, to discover the biomarkers, and even to develop the drugs. So what kind of sensing technologies can help us achieve this goal? Next slide, please. So I think one of the solutions could be to develop a multiplexity, high multiplexity biosensing technique, because it can enable an easy, rapid, and precise detection of various target chemicals simultaneously in a biosample. So this can also be used in blood testing, cancer screening, genetic testing, and wearable sensing. To enable high multiplexity biosensing, we need some kind of a fingerprint for the target molecules. And next slide, please. So a good fingerprint for the biomolecule is Raman spectroscopy. So Raman measures the vibrational modes of the chemical bonds in a molecule. So considering every molecule has a unique set of chemical bonds, a Raman spectra is a fingerprint for the molecule. Every molecule has a unique Raman spectra, which is different than any other molecules. So for the Raman measurement, you can also just shine laser onto the molecule and you detect the scattered light spectroscopy spectrum, and you can get a Raman spectrum. So for the Raman spectra, it's non-invasive and it's also label-free. So the measurement here is very simple. Next slide, please. So we then try to use Raman to demonstrate the high multiplexity. So in this case, we use a sample of a mouse brain slice. We think it's complicated enough, and it can actually test the capability of Raman in detecting multiple molecules. So next slide. Next slide. So over here, we can see if we just perform a 1 second Raman measurement on the mouse brain slice, we can identify the relative concentration of 17 molecules in the mouse brain slice. And as far as we know, this is the best multiplexity in the molecular level among rapid detection techniques. In addition, if we perform a hyperspectral Raman imaging, we can obtain the high resolution image of the distribution of each of these 17 molecules. And here I'm showing 2 examples of the molecules. So by studying the correlation between the distributions of these molecules, it can provide important information for brain study. Next slide. So now we're wondering how 2D material can help with this process. So in our measurements of brain slices, we contacted a layer of graphene with the molecule. And then we try to understand the signal to noise ratio for the Raman spectrum. Next slide. So now you can see in the red block, I'm showing the signal to noise ratio for the measurement with graphene, and the green block shows the measurement without graphene. You can see apparently with graphene, the signal to noise ratio is much better compared to the case without graphene. So graphene can enhance the signal to noise ratio for the brain Raman measurement. Next slide. So with this tool, with the graphene-assisted Raman spectroscopy, we try to understand how it can help with the Alzheimer's disease diagnosis. So from our collaborators, we obtained 2 types of brain slices. They're from the mice with Alzheimer's disease and without the disease. Then we just measure Raman spectra on these brain slices. And for part of the measurement, we contacted a layer of graphene with these brain slices. And now my students, Yang Wang, try to use machine learning to classify these Raman spectra, AD versus non-AD. So next slide. So the results are shown here. So you can see here I'm showing the metrics of machine learning, accuracy, AUC, sensitivity, and specificity, and for different machine learning algorithms. The red blocks here again shows the result for the measurement with graphene, and the green blocks shows the measurement without graphene. You can see apparently for the measurement with graphene, the machine learning performance is much better compared to the case without graphene. So for example, if we focus on accuracy and SVM algorithm support vector machine, we can see with graphene, the accuracy is more than 99%, but without graphene, the accuracy is less than 75%. So next slide. So now we can see using graphene-assisted Raman spectroscopy, it can provide an optics-based, simple yet effective tool to identify AD. So this is very exciting. We can identify AD with high accuracy. But we want to see if machine learning can tell us something more about this simple classification of Raman spectra. So next slide. So it turns out, if we use this very simple algorithm, SVM, support vector machine, we can obtain this so-called spectral feature importance. So this means the importance of each wave number in classifying AD versus non-AD. So what's the use of the spectral feature importance? Well, if you consider that Raman spectra are fingerprints for the molecules, so the spectral feature importance should have a good correlation with the Raman spectra of the biomarkers for Alzheimer's disease, right? So next slide. Yeah, next slide. Yeah. So now let's examine the known AD biomarkers. And here I'm showing 4 molecules. Actually, there are 4 proteins, A beta and tau proteins. The black dashed lines show the spectral ranges of their Raman peaks. So we can first calculate the spectral overlap between the Raman peaks of the biomarkers and the spectral feature importance peaks. We can get a peak matching score. We can also directly calculate the cross-correlation between the Raman spectra of the biomarkers and the spectral feature importance map. So we can get a cross-correlation score. If these scores are higher, that means these molecules are more important to AD. So actually, if we look at these scores, they are very high, much higher than a random molecule, which only has a few percentage of scores. So this matches our expectation. In addition, if we compare oligomeric forms with monomeric forms, we can see the oligomeric form always have higher scores compared to the monomeric forms for both A beta and tau, and for both peak matching score and cross-correlation score. So this again matches our expectation because oligomeric forms are considered more important to AD. So with the spectral feature importance, we can also try to identify several other molecules which are potentially biomarkers. So here in our study, we identified 3 molecules, trialing, phosphatidylcholine, and actin. And you can see their Raman spectra are highly correlated to this spectral feature importance. Actually, other biochemical studies have verified that these molecules are indeed highly correlated to AD. So far, what we have seen is the so-called positive feature importance. So next slide. So positive feature importance here, so if you go to the previous slide. Yeah, so positive here means these features are more represented in the AD samples. In addition to positive feature importance, we can actually also get the negative feature importance, which means these features are more represented in the non-AD samples. So the negative feature importance can also be very helpful to identify several biomarkers, negative biomarkers, and they could also identify, they could also help to identify some information of drug molecules. So next slide. So here with the negative feature importance, next slide. We actually identified several other molecules, for example, cytochrome and glycogen. They have high correlation with the negative feature importance. And actually, biochemical studies have also verified that these 2 molecules are indeed highly inducive to brain functions. The next slide. So now we can see by using Raman spectroscopy combined with machine learning analysis, we can provide a rapid pre-screening of biomarkers, both positive and negative biomarkers. So next slide. So in addition, with this Raman tool, remember, we can perform a hyperspectral Raman imaging. So this enables us to identify, to obtain high resolution image of the brain slices. So here in this study, we map the hemisphere of a brain slice. As you can see on the right, the color of each pixel shows their correlation with AD. So the brighter the pixel is, the more correlated with AD for this pixel. And therefore, we can identify the AD-sensitive brain regions with high resolution. So for example, if we look at some highlighted brain regions, next slide. We can see there are some regions like cortex, hippocampus, and amygdala that are highly correlated to AD. And you can also see there are some dark regions. For next slide. So for example, what is shown here is thalamus and hypothalamus, and they're not that sensitive to AD. So this provides us important information on the brain region correlation with AD. So next slide. So far you can see by using Raman assisted with 2D material like graphene, and together with the machine learning analysis, we can greatly accelerate the study of AD in terms of diagnosis, the understanding of pathology, drug development, and therapeutics. In addition, if you actually think about what we did, we simply perform Raman measurements with machine learning. So this technique is not limited to AD, it's not limited to brain slices. it can actually be widely applicable to study other types of diseases, biotissues, biofluids, and also human samples. The next slide. So recently, we used a similar strategy and tried to understand this coronavirus. So in particular, we're focusing on this structure called RBD, receptor binding domain, which is a protein structure on the surface of this coronavirus. This RBD is actually the key structure for COVID-19 infection. And actually, if there's some mutations of this virus, typically there's a mutation of the structure for RBD. So to understand the structure for RBD is very important, and it directly affects the development of vaccines and neutralizing antibodies. So here in our study, we measure the Raman spectrum for RBD of SARS-CoV-2 virus. And for comparison, we also performed the measurement of RBD from another coronavirus, which is MERS. So if you just look at these two Raman spectra, you can see there are some differences. And these differences are due to the different proteins of these RBDs. So we know a protein has 4 levels of structures. In the primary level, there is a chain of amino acid. So the different compositions of amino acid can contribute to the difference of their Raman spectrum. So next slide. So here we are also using machine learning to classify the Raman spectra of RBDs from SARS and MERS. So you can see their metrics are very high, over 95% for all the metrics. Next slide. In addition, we can also obtain the spectral feature importance. So you can see in this plot, the spectral feature importance have several peaks, and we can do some analysis for these peaks. So for example, if you, next slide. So for example, if you look at these peaks, this corresponds to an amino acid called phenylalanine. It has peaks for phenylalanine. So that means the composition of phenylalanine in SARS and MERS RBDs are very different. So if we want to confirm this, we can look at the protein sequencing result. So next slide. So from the sequencing result, which can be considered as ground truth, indeed, we can see phenylalanine has a very different composition in SARS and MERS RBDs. And the similar case goes for some other amino acid. Next slide. So you can see these peaks correspond to tryptophan and histidine. Next slide. So you can also see tryptophan and histidine has very different compositions in SARS and MERS RBDs. On the other hand, if you look at another wave number, next slide. So this wave number corresponds to tryptophan. So you can see the feature importance of tryptophan is almost 0 here. So that means the tryptophan composition should be very similar for SARS and MERS RBDs. Next slide. So if you check the sequencing result, you can see indeed they are very similar to each other. So next slide. So far we can see by using Raman measurements with machine learning analysis, this can greatly facilitate our understanding of the nanostructures of proteins. Next slide. So in addition to RBDs and coronavirus, we also extended our study to other types of viruses, including flu virus, real viruses, and so on. So we can obtain high accuracy in classifying these viruses according to their Raman spectrum. Next slide. So for example, if we consider flu A versus flu B, we can achieve accuracy over 99%. If we look at subtypes of flu A, for example, H1N1 and H3N2, the accuracy is over 96%. In addition, if we just look at the point mutation of one particular subtype of flu A, we can still achieve a high accuracy over 90%. So next slide. So with this Raman sensing tool, a machine learning framework, and together with a virus data bank, we can potentially build a worldwide virus surveillance network. We can build nanosensors and put it in different locations, like in the hospitals, airports, and schools, even in the farms and wilderness. And these sensors can form a global internet of sensors. It can give us early alarm of the potential virus outbreak and the potential mutation of a virus. Next slide. So far, we have been using Raman spectra and with machine learning to analyze Alzheimer's disease and to understand viruses. Next slide. And very recently, we also tried to use a similar strategy and understand another complicated disease, which is pancreatic cancer. So pancreatic cancer currently has the 4th leading cancer death in the United States. And 8 people diagnosed with 8 in 10 people diagnosed with pancreatic cancer already has the cancer cells spread out of the pancreas. And the 5-year median survival rate is less than 10%, which is among the worst among all cancers. So you can see the early diagnosis of pancreatic cancer is actually a big issue. And this is also why many celebrities like Ruth Bader Ginsburg and Steve Jobs also died of pancreatic cancer. So recently we established a collaboration with MD Anderson, and we try to use our technique and contribute to the understanding of this complicated disease. Next slide. And next slide. So far, if you actually think about the researchers in the biomedical field actually developed lots of advanced sensing techniques, including mass spectrometry, MRI, ELISA, and so on. It would be actually better to combine all of these techniques, including Raman, to build a multimodal sensing platform. Next slide. And combining all of these techniques, we can actually improve the accuracy for biomarker discovery. Next slide. So recently, funded by NSF and NIH, and in collaboration with Penn State, MIT, Massachusetts General Hospital, Harvard Medical School, and Rice, we established a new project called Momenta platform for Alzheimer's disease. So Momenta here stands for multimodal optical mechanical electrochemical nanosensor with 2D material amplification. Next slide. So with this Momenta platform, we are also targeting multiple biosamples from non-invasive to minimally invasive biosamples, including blood, tear, and saliva. So this will actually simplify the overall diagnosis process for Alzheimer's disease, which can really benefit the people in the rural area and financially disadvantaged groups. Because data have shown that the death rate due to Alzheimer's disease in the rural area is over 3 times higher than the urban area. And the reasons include the lack of timely diagnosis and primary care. So hopefully with our Momenta platform, we can simplify the overall diagnosis process and really benefit this group of people. So next slide. So far I have shown some examples of biosensing, and in these biosensors, actually 2D material plays a quite important role. And actually 2D material can be a very good sensor material because they are atomically thin and they can be very sensitive to anything sitting on their surface. In addition, the 2D material are atomically flat and there's no dangling bonds on their surface. So when they interact with the molecules on their surface, the interaction will be very robust. And this is also why the 2D material has also been widely used for biosensing. So for example, for SARS-CoV-2 virus detection, 2D material including graphene and molybdisulfide, tungsten diselenide have provided high sensitivity in detecting these viruses. Next slide. So we actually have a large group of 2D materials, and they span a wide electromagnetic spectral range. And for different electromagnetic spectral ranges, we can have different types of 2D material that can be particularly useful for these spectral ranges. So in addition to these natural 2D materials, we can also make designer 2D materials. So we can make some artificial structures and approach their properties to what you desire. Next slide. So for example, for designer 2D materials, we can build heterostacks and homostacks of 2D materials. We can also make an artificial mirror symmetry broken structure called Janus monolayer. We can also introduce atomic doping, atomic defects, and we can also change their shapes. And these have proved to be efficient ways to tune the 2D material properties. So for the next maybe 5 minutes or so, I will give you a quick overview or a quick survey of our recent study for making some designer 2D materials. So next slide. So the first structure I want to introduce is this atomic substitution in TMD materials. In particular, we're looking at nitrogen substituting the sulfur side in tungsten disulfide. And this is monolayer tungsten disulfide. And this experiment was actually performed at Penn State NanoFab. So we used the remote nitrogen plasma in PELD, and we treated with tungsten disulfide. And after the treatment, if we measure XPS, as you can see, we can see a tungsten nitrogen bonding over here. This is an indication of the nitrogen substitutional defects. And we can further confirm this defect by STEM imaging. So in the plot on the right, you can see these red arrows actually show the nitrogen substitutional defects. Next slide. So for us, what's really interesting is there is a new photoluminescence peak generated from the nitrogen substitutional defects. So this PL peak energy is actually at 1.59 eV, and this is well separated from the free excitons of tungsten disulfide. Now, if we look at some other defects in tungsten disulfide, for example, the most common sulfur vacancy. Now, sulfur vacancy also has PL emission, but its energy is very close to the free excitons. And you can see at room temperature, typically it's very hard to distinguish the two peaks. So this nitrogen substitutional defects, on the other hand, at room temperature, it has a well-separated peak from the free exciton, which shows its uniqueness. Next slide. So we then try to understand better about this new PL peak. So we performed STM and STS measurements on the sample in collaboration with Dr. Sabin Haas at Oak Ridge National Lab. So we can see over here, there are nitrogen substitutional defects, there are pristine sites. If we measure STS on these sites, we can see nitrogen substitutional defects actually provide a new defect peak in the band gap of tungsten disulfide. This is very different from the pristine samples. In addition, if we look at sulfur vacancy site, you can also see the sulfur vacancy site has a different STS compared to nitrogen substitutional defects. So this new defect band is contributing to the new PL peak for the nitrogen substitutional defects. Next slide. So far we have seen we can do atomic substitutional defects for 2D material. In addition, we can extend this substitutional defect to the entire sublayer of the 2D material, so we can make this Janus structure. So in particular, in our work, we are making this Janus MOSSE. So if we start with MOS2, perform a Janus conversion, the top layer of sulfur atoms will be converted to selenium atoms. In addition, if we start with a bilayer MOS2, we can end up with a heterostack of MOSSE Janus with MOS2. The next slide. So we then found something interesting about this heterostack. So for example, if we measure the low frequency Raman spectra, you can see the plots over here shows the low frequency or interlayer shear mode and a breathing mode for different stacking of this heterostack. So these interlayer Raman modes has the entire layer of the 2D material vibrates as a whole unit compared to the adjacent layers. So we can understand these low frequency or interlayer Raman modes using the linear chain model. Next slide. So in the linear chain model, we can calculate the frequency of the Raman spectra using this equation. So here K is the van der Waals coupling between the two layers. So you can see from the frequency that's measured by Raman and the reduced mass, which is the M in the equation, we can actually calculate the K, the van der Waals coupling strength. Next slide. So now we can obtain the van der Waals coupling strength in the Janus heterostack, and we can also calculate the corresponding van der Waals heterostack, van der Waals coupling strength for the MOS2 homostack. And we can compare the two. Next slide. So this table shows the comparison result. So the delta K over here are actually all positive. So this means the Janus heterostack has a stronger interlayer coupling strength compared to the MOS2 homostack. Now these results are remarkable because it is the first time that people have ever seen an enhancement of the coupling strength for the van der Waals heterostack compared to the corresponding homostack. If you just have a natural 2D material build a heterostack, this will not occur. And the fundamental reason for such an enhancement of the coupling strength is due to the Janus monolayer. The Janus monolayer breaks the mirror symmetry, and it provides a vertical dipole, which effectively tune the interlayer coupling strength or the van der Waals coupling strength with the adjacent materials. Next slide. So speaking of heterostack, recently we are also looking at this 2D metal heterostack. And this is a collaboration with Penn State Merced Center. You can see the material structure looks like this. So we collaborated with Josh Robinson's group at Penn State and wrote this material. We can start with silicon carbide and perform epitaxy of graphene on silicon carbide. After the graphene epitaxial growth, we can introduce a layer a few layers of 2D silver atoms in between graphene and silicon carbide. Next slide. So now this has been confirmed by STEM image on the cross-section of the sample. So you can see clearly there's 2D atomic layers of silver atoms formed between graphene and silicon carbide. Next slide. So for us, what's really interesting about these samples lies in their Raman spectrum. So if you look at the Raman spectrum for silicon carbide or graphene on silicon carbide on the bottom two spectra, you can see there's not much going on. However, as soon as we introduce this 2D atomic layers of silver, you can see these Raman modes are strongly enhanced. And what's more, these Raman modes does not look like the normal Raman modes you can measure. So for a normal Raman modes, typically they have the symmetric Lorentzian line shape. However, in this case, the Raman spectra the Raman peaks are apparently asymmetric. Next slide. So these asymmetric modes are actually called Fano line shape, and they are the origin of these Fano peaks are in the interference between a discrete phonon mode and a continuous mode. So the higher the coupling strength is, the more asymmetric this mode is. So actually in this 2D silver sample, we observe a very high asymmetry factor, which means the coupling strength for these modes are very, very strong. So if you look at the right plot, this benchmark the asymmetry factor for different types of samples in their phonon modes. So for this 2D silver structure, you can see we achieve a record high asymmetry factor. It's order of magnitude higher than any other materials. So again, with this artificial structure, we can achieve ultra strong quantum interference for the phonon modes. So next slide. So in addition to phonons and linear optical modes, we also took an interest for the nonlinear optical mode. Particularly, we have an interest to try to enhance the second harmonic generation, or SHG, for TMD materials. We know a monolayer TMD like MOS2, due to the broken inversion symmetry, it has SHG signal. However, due to the very, very small thickness, the light matter interaction is not enough, so the SHG signal is limited. So then we try to see how we can further enhance the SHG signal for MOS2. Next slide. We then thought about a method. We can just roll it up. So if we form this 1D nanoscroll, the second order amplitude will superpose with each other in this nanoscroll, and the overall SHG intensity will be very strong. Next slide. So in our experiments, we fabricated this 1D nanoscroll using a solvent evaporation process. You can see in this plot, and here in the center, there is MOS2 monolayer, but at the edge, you can see there are 1D nanoscrolls. Next slide. Next slide. Now, if we map the SEG intensity for the sample, we can see apparently the nanoscrolls give you a higher SEG intensity compared to the monolayers. Next slide. So if we actually look at the polar plots for the SEG signal for monolayer and nanoscroll, we can see the nanoscroll actually gives you about 100 times stronger SEG signal compared to the monolayer MOS2. So by forming this nanoscroll, we can indeed effectively enhance the SEG signal. In addition, these SEG signals are chirality dependent. So we can control the polar plot orientation and shape by controlling the chirality of these nanoscrolls, which means the rolling direction of these nanoscrolls. So next slide. So in addition to phonons and photons, we also took an interest for magnons in the van der Waals materials. The magnons are a collective excitation of the spin structures for magnetic materials. So in particular, we are interested in this van der Waals antiferromagnet, which is called the manganese bismuth telluride, or MBT. So we can actually exfoliate these materials down to a few layers. In this case, I'm showing the Raman spectra for 5 layers of this material. And then you can see in this Raman spectra, there are lots of peaks. Next slide. So if you focus on these peaks, you can see when we apply magnetic fields, there's not much going on. These peaks do not change. Next slide. However, if you focus on this very small frequency range, you can see these peaks, their frequency actually change a lot with the applied magnetic field. Next slide. So for example, you can see here, there is a big change of the frequency for these low frequency Raman modes. And this shows that these modes are actually magnons rather than phonons. So next slide. All right, so far we have seen that by making these designer 2D materials, next slide. So you can click it 4 times. So next slide, yeah, that's it, yeah. So we can see if we perform this heterostacking and homostacking of 2D materials, we can introduce ultra strong quantum interference. If we make a Janus monolayer, we can tailor the van der Waals coupling strands with the adjacent materials. If we introduce atomic doping or defects, we can generate new optical emission peaks. And if we change the shapes of the 2D material, we can achieve enhanced and chiral optical nonlinearity. So next slide. So basically, these materials, designer 2D materials, are essentially new materials. And with these many designer 2D materials, a very practical question comes out, which is how to characterize these materials quickly, accurately, and in pronto in devices. Next slide. So when we try to integrate 2D materials into some optical or photonic structures, a very important parameter we need to know during the design process is their refractive index, including the real part N and imaginary part K. Next slide. So conventionally, we can measure the N and K using the ellipsometry. So in the ellipsometry measurements, we can have incident light with a large incident angle. And then we can measure the reflection coefficient with different polarizations. And as a result, you can obtain these two parameters, psi and delta. Next slide. So the psi shows the amplitude of this ratio, and delta shows the phase of the ratio for different polarizations. So the psi and delta is what you measure from ellipsometry. And your next goal is to obtain the N and K from the measured psi and delta. Next slide. So in particular, psi and delta are related to N and K with this Fresnel equation. So if we actually know the N and K of a material at the interface, we can use the Fresnel equation to calculate the psi and delta. However, for the ellipsometry problem, it is an inverse problem. So what you measure is psi and delta, And then you need to solve the inverse problem to obtain the N and K. Next slide. And next slide. And one more. Yeah, so you need to solve this inverse problem. So if you look at the Fresnel equation, they're actually not trivial. There's no analytical solution for this inverse problem. And therefore, we need to use some model fitting method to obtain the N and K. Next slide. So actually, this is the first major challenge for the conventional ellipsometry, which is the intensive model fitting. So next slide. So to fit the psi and delta measured by ellipsometry, we need to use several oscillator types. And this requires you to have a basic understanding of the physics properties of this material, so you can choose the correct oscillator types. In addition, there are lots of fitting parameters for you to choose. And here I just list a few. And a small change of the fitting parameter could lead to a big difference in the fitting result. So for example, what I'm showing here is the psi and delta for MOS2. Now, if you use six Hawk-Lorentz oscillators, now you can get the N and K like this. Next slide. And next slide. So now if I just change the oscillator number to 5, you can see the fitted N and K will be very different for the previous result. Next slide. And you can see there is a big feature that's missing for the N and K. So that's the first major challenge, the intensive model fitting. Next slide. The second major challenge for the conventional ellipsometry is there is a need for the simple and known structure for the measurement. So let's say you want to measure the MOS2 N and K. You can just prepare a 3 nanometer thick MOS2 onto a bare silicon substrate. This is okay. This is considered as a simple and known structure. Next slide. And next slide. However, if you just use another substrate, for example, 300 nanometer silicon oxide on silicon, which is a very conventional substrate, this is already not okay because this substrate is complicated. Next slide. So this is considered as a complex structure. Next slide. So in addition, if you still have 3 nanometer MOS2 and you put it on a simple substrate, however, you don't know what this substrate is. This is not okay either because this is an unknown structure. Next slide. So overall, you can see another big challenge for the conventional ellipsometry is the need of simple and known structure. Next slide. The third big challenge for the conventional ellipsometry is there is a special setup that's needed, which is an ellipsometer. And this requires a large incident angle, which is not easily implemented in the lab microscopes, which typically has a normal incidence. Next slide. So to solve the three major challenges for the conventional ellipsometry, we think deep learning could help. Deep learning recently has shown its great power in solving scientific problems. So for example, we all know this AlphaFold has done an excellent job in solving the protein folding problem, which is a long-term challenge in the field of biology. And very recently, deep learning also shows its power in solving material science problems. For example, this genome, which is a deep learning neural network, can predict as many as 2.2 million stable structures. In addition, with the help of a robot, it can successfully synthesize 41 types of materials within 17 days. So these, for sample growth, we all know this is a very efficient growth process. Next slide. So in our case, we try to use deep learning to assist the measurement for refractive index. So we build a neural network that we call Reflector net. Next slide. The Reflector net is essentially an encoder-decoder convolutional neural network. The output of Reflector net is directly the N and K of the material. Next slide. And next slide. So we can see the first challenge for the conventional ellipsometry is actually resolved. So in this case, we don't need intensive model fitting, and actually we don't need any model fitting. The output of reflector net is directly NNK. Next slide. So for the input of reflector net, we need 5 pairs of reflectance spectra, and each pair of the reflectance spectra contains a reflectance spectra with the target material and without the target material. And the 5 pairs includes different types of structures. For example, you can have different thicknesses for the target material. You can have different types of substrate and different combinations of substrate materials. So for these substrates, they can actually be quite complicated. So you can see actually the second challenge of the conventional ellipsometry is also resolved. We do not need to have a simple and known structure. We actually do not need to have any knowledge about the structure. All we need to know is the reflectance spectra and 5 pairs of them. Next slide. Also, the third challenge, the spatial setup, is also resolved. Because for reflector net, we just need a normal incidence spectrum, which can be easily implemented in the lab microscopes. Next slide. So now let's look at the data set for the reflector net. Next slide. So for the ground truth, the NNK of the material, we are using the C2DB database. So we obtained 1,600 material entries from the database. We further augmented these data to have NNK as long as they fit the Kramers-Kronig relation or the KK relation. Next slide. For the input data, we used a simulated dielectrics using the Selmier formula. And overall, we randomly generated 450,000 multi-layer stacks. And then we calculate the reflectance spectra for these structures using the transfer matrix method, which is a very rapid and precise way to obtain the reflectance spectrum. Next slide. So for all of these data, we use 95% of them for training, 5% for validation. And for the testing set, we generated an additional 10,000 stacks with completely different target materials. So this really tests the capability of reflector net in recognizing completely different materials. Next slide. So now let's look at the performance of reflector net. So here I'm showing some examples from the training set, validation set, and independent testing set. So in these plots, I'm showing the real part N, which is showing the red curve, imaginary part K, which is the green curve, and the ground truth is shown as the solid curve, prediction is shown as the dotted curve. So in all of these cases, you can see the ground truth matches very well with the prediction. Next slide. And next slide. So we then generated 2 metrics to evaluate the overall performance of reflector net. So these metrics are RMSPS, the root mean square percentage score, and PCC, Pearson correlation coefficient. So you can see their values are very high, especially the PCC. So this shows that the reflector net is very good at recognizing the overall shapes and trend of the curves. Next slide. So we then also tested the capability of reflector net in predicting experimental data. So here we performed an experiment. We exfoliated MOS2 onto 2 types of substrates. They're the bare silicon substrate and 300 nanometer silicon oxide on silicon substrate. We obtained different thicknesses for the MOS2 flakes, and then we measured their reflectance spectra. We use them as input and let reflector net to predict the N and the K, as you can see on the right. So the ground truth over here are the ellipsometry measured N and K. So you can see there is a good matching between the prediction and the ground truth. Next slide. So we also tested other materials using our experimental data, including MOSE2, WS2, and WSE2. So in all of these cases, you can see there is a good matching between the prediction and the ground truth. Next slide. So in addition, we also realized that reflector net actually learns some physics. So we know the N and K of a material is not independent from each other. They're related to each other by the Kramers-Kronig relation or the KK relation. If we know the N, we can use KK relation to calculate K. And if we know K, we can use KK relation to calculate N. So when we train the reflector net, we did not provide any information about KK relation. We simply let a reflector net to learn both N and K. And however, we actually realized it learned the KK relation. So for example, on the right, I'm showing a material, its real part N, imaginary part K, and predicted value and the ground truth. So now if we use the predicted N and a KK relation to calculate a K, next slide. So we can get the curve like this. So this KK relation calculated K. So you can see the KK relation calculated K, the black dot curve, matches very well with the reflector net predicted curve, especially at the center of the spectral range. And this is because we have a denominator omega prime minus omega in the KK relation. So this means the prediction of a value at a particular frequency is more accurate when the adjacent values are available. So that's why the prediction at the center of the spectral range is more accurate. At the edge of the spectral range, you can see there are some deviations, and these are inevitable because the values outside the spectral range is not available. And for the KK relation, we also need to have an integration go to infinity. So there are inevitably some deviation. In addition, if you look at the KK relation, if you look at the reflector net predicted K, you can see it matches better with the ground truth. And this is actually another advantage of using the reflector net rather than KK relation for obtaining the N and K. So next slide. So far we have seen we can use the reflector net to obtain N and K for a new material. So this solves some some challenges for the conventional ellipsometry. But then we realize for the input of the reflector net, we still need different types of structures for the materials. So next slide. So we need multiple structures as input. This will not be practical when we try to predict the N and K for a material in optoelectronic in the device. Next slide. So typically, we want to integrate 2D materials into some devices. For example, we integrated onto electronic device. We want to apply bias voltage, and we try to study the N and K in response to these bias voltages. And in some other cases, we may want to study the N and K with a temperature change. So during the operation of these devices, there's no way you can obtain different types of structures. So we then realized there's a need of a new reflector net to capture the in-optoelectronic prediction of the refractive index. The next slide. So we then developed a new network, and that we actually used this recurrent neural network, RNN. So we call this Reflector RNN. It can predict the evolving 2D material and thin films. For example, we can predict the N and K in response to the bias voltage, temperature change, and strain. Next slide. So this reflector RNN works like this. Next slide. So first, for the input, we need a base N and a K and the base reflectance spectrum. Next slide. So then you can apply external stimuli. For example, you can apply bias voltage, and then you measure the modulated reflectance spectrum. Next slide. And then the reflector RNN will give you the modulated N and K. You can actually have a series of change or a series of modulation of external stimuli, and the output will be a series of N and K. Next slide. So now let's look at the performance of reflector RNN. So still root mean square and Pearson correlation coefficient. So you can see their values are very high, especially the PCC is as high as 99%. In addition, you can see from training set to validation and testing set, there's no degradation of the performance of reflector net. So this actually shows the capability of Reflector RNN in recognizing new materials. Next slide. So in addition, here I'm showing 4 examples of materials with a series of external stimuli and their corresponding N and K. And again, the solid curve shows the ground truth, the dotted curve shows the prediction. So you can see there's a very good matching between the prediction and the ground truth. Next slide. So with this reflector net and reflector RNN, they will have broad applications. Next slide. So potentially we can use them to characterize designer thin films and designer 2D materials. Next slide. So first, I want to mention with the reflector net and reflector RNN, we can easily capture the in-plane anisotropy for a material. Conventionally, if we use ellipsometry to measure in-plane anisotropic 2D material, this is not very trivial because of the oblique incidence. However, for reflector net or reflector RNN, we're just looking at the normal incidence, and to capture the in-plane anisotropy, we can simply change the polarization of incident light and reflected light. Next slide. And you can click 2 more times. Yeah, so in addition, we can obtain the in-operando change of Rn and K for a material in complex device structures. So this really enables us to study the change of the material properties in response to doping, strain, temperature change, and defects. And in our studies so far, we are focusing on the spectral range between 400 nanometer to 800 nanometer in wavelengths. But our model can be easily extended to other spectral ranges for different applications. So next slide. So with this, I would like to stop here and really acknowledge our collaborators involved in the work I've described, especially many collaborators at Penn State, and also acknowledgement to my students who actually performed the work. And here I would also like to mention we have multiple openings for postdocs and PhD students. So if you're interested in our types of research, please feel free to contact me. And finally, thanks to our sponsors, and thank you for your attention. Happy to answer questions now.
Sheng-Shi, does anyone have any questions?
I agree today.
It doesn't look like there are questions, Sheng-Shi, so thank you so much for your time. And have a good rest of your afternoon.
Thank you.
Thanks, Sheng-Shi. Sorry about the tech issues.
Sure. Yeah, thank you.
All right. So that's it for this semester then, I guess, Kelsey. So I'm going to email somebody to invite for January, a colleague that I know.
Oh,
So
okay.
he will agree, and then we should be set for spring. Right,
Oh, awesome.
because we just have those other 3 dates that are already set. Yeah. And then